Okay, so why is the function f of xy equal to 2x over x squared plus y squared not continuous? All right, well, let's see. Obviously, the problem place would be 0, 0. So here's the example. Here's the function f of xy. I'm going to let it be 2x y over x squared plus y squared. And this is if xy is not equal to 0, 0. And I'm just going to say it's 0 if xy is equal to 0. Okay, so in order to show continuity, we have to do the continuity test. And the continuity test is as follows. 1, we have to show that f of 0, 0 exists. Well, it does. F of 0, 0 is defined to be 0. 2, the limit as xy approaches 0, 0 of f of xy exists. So that for us is a big question mark. So we have to show that exists. So we need to do that. Okay, so clearly everywhere other than 0, 0, I can put a number in and I'm good. The only issue is at the origin 0, 0. So now I want to check for the limit. Now remember we said that when you're checking to see whether or not a function of two variables has a limit, you have to look at all the different ways it can approach the origin or whatever point that you're looking at. So what I've done in the past is I've gone along the x-axis, the y-axis, maybe I went along y is equal to 2x. Here I went along the x-axis, I went along y is equal to 4x squared. I just need to find something that's going to give me an idea of whether or not this limit actually exists. So as I look at this function, I see that I have an x and x in the numerator. So that is of the power x, in a sense, two things. So that's like a squared power. And in the bottom, I already have a squared and a squared. So I now basically have something squared over something squared. So the right order is okay. So now if I could just keep it so that they stay within the same parameters. So I'm going to choose to take the limit as xy goes to 0, 0 along the line, the lines y is equal to mx. So m here is any real number. So it could be y equals x, y equals 2x, y equals a half x, y equals 12x. Okay, so when I take that limit, I now get the limit as x and y is mx goes to 0, 0. In the place of x, I have x, but in the place of y, I'm going to put mx. And then down here, I'm going to get x squared, and over here, I'm going to get mx squared. So now this is the limit. as x mx approaches 0, 0. And in the numerator, I get 2m x squared. And in the denominator, I get 1 plus m squared x squared. So that is the limit as x mx approaches 0, 0. And notice I can cancel out the m squared and I get 2m over 1 plus m squared. Now that's a problem, because if I go along, if m is 1 and I go along the line y equals x, I'm simply going to get the limit as 1. But if I go along m is equal to 3, then I'm going to get 6 over 10. So for each m, I get a different limit. So for each m, and that is an approach along a different line, we get a different limit. So that means that the limit as xy approaches 0, 0 of the function 2x y over x squared plus y squared does not exist. And since the limit does not exist, that means the function f of xy equal to 2xy over x squared plus y squared is not continuous at the point 0, 0. So if it's not continuous at one point, we can't say that it's continuous everywhere. Okay. All righty, on page 981, this is page 9. Oh, page 990 is missing. 980 is missing. Oh, ho, ho. Okay, so we said that this is a more difficult problem. All right, so let's determine whether or not this function is continuous at 0, 0. Okay. Is f of xy equal to x to the 4th plus 2x squared plus 2y squared plus y to the fourth over x squared plus y squared continuous at 0, 0. Oh, wait a minute. Oh, this is, I screwed up. This is if x, y is not equal to 0, 0. And it's 2 if x, y is equal to 0, 0. Okay, so is that function continuous at 0, 0? Okay, so now we can do, so we got to do the continuity test. Number one, f of 0, 0 is defined to be 2. So therefore, that checks. Okay. Now we need to check to find the limit as x, y approaches 0, 0 of my function f of x, y. So we got to find this. Okay. I can't imagine if I was teaching in the classroom right now, my wrist is just hurting and I'm only using the table. Okay, so we're going to try 2 different ways and see what we get. Okay, so we're first going to try going along the line y equals mx. So for the continuity test, we're going to test the limit. So we're going to check the limit as xy approaches 0, 0 along the line y is equal to mx. Okay, like we did before. So when we do that, we get the limit so this now becomes x mx. So now I'm going to get x to the fourth plus 2x squared plus 2mx squared plus mx to the fourth. Uh-oh, get rid of the equals. There shouldn't be equals there. Over x squared plus mx squared. So there's no more y, so I'm just going to write the limit as x approaches 0 at this point. I'm just going to make my life easy. So this now becomes x to the fourth times 1 plus m 1 plus m to the fourth. That's from the last term. You see it, 1 plus m to the fourth. Plus, I can factor out a 2x squared. And that leaves me 1 plus m squared divided by 1 plus x squared times 1 plus m squared. So I can factor out x squared. So that's the limit as x approaches 0. So when I take x squared out the first term, I get x squared times 1 plus m to the 4th plus 2 times 1 plus m squared divided by 1 plus m squared. And so these, as x goes to 0, the first term goes to 0 and gets killed off. And then the last two terms just give me 2. So I get equals 2. So that's nice. It does not depend on m. Okay, so far that's looking good. Looks like the limit might be 2. So let's check the limit as xy approaches 0, 0. And this time I want to go along the parabola. Y is equal to x squared. So I'm going to try another path and see if I get something different. So now I get the limit and so y is equal to x squared. So now I'm going to get x to the 4th plus 2x squared plus 2, y is x squared squared plus y to the 4th. So that's x squared to the 4th power divided by x squared plus x squared squared. So now this is the limit as x approaches 0. I have x to the 4th and another x to the 4th. So that gives me 3x to the 4th. So I have x to the 8th plus 3x to the 4th plus 2x squared divided by is that right? Divided by x squared plus x to the 4th. So let's factor out x squared. That's the limit as x approaches 0 of x to the 6th plus 3x squared plus 2. And I factor out x squared, and that leaves me 1 plus x squared. And as x goes to 0, I get 2. Woohoo! Okay, so it's looking real good. The problem is I can't just keep checking paths because there may be a path that it doesn't work. So I technically need to use the definition of the limit to prove that it's 2. So now we need to use the definition of the limit to prove it is 2. Okay, so the definition of the limit, you remember, said that the the limit as xy approaches x naught, y naught of f of xy equal L if for all epsilon greater than 0, there exists a delta greater than 0, such that when the 0 less than the square root of x minus x naught squared plus y minus y naught squared is less than delta, then the absolute value of f of xy minus L has to be less than epsilon. So I got to prove that. Oh, okay. So we need to prove, so for us, that is, for all epsilon greater than 0, there exists a delta greater than 0 such that 0 less than x naught is 0, 0. So we just get the square root of x squared plus y squared is less than delta implies the absolute value, and f of xy is pretty icky. X to the 4th plus 2x squared plus 2y squared plus y to the 4th divided by x squared plus y squared minus 2 has to be less than epsilon. So that's what we got to show. Okay. All right. So let's assume that 0 is less than the square root of x squared plus y squared is less than delta. Okay. Okay, so x squared is less than x squared plus y squared, less than or equal to x squared plus y squared. And y squared is less than or equal to x squared plus y squared. I'm still working on this. Okay. So the absolute value of x to the 4th plus y to the 4th over x squared plus y squared. Well, that is less than, if I add these even terms in, x to the 4th plus uh, x to the fourth, this is x squared squared. So I can write this as it actually equals x squared squared plus y squared squared over x squared plus y squared. And that's less than or equal to, in the place of x squared, I'm going to write x squared plus y squared squared plus x squared plus y squared squared. And that's still over x squared plus y squared. And that is equal to 2 times x squared plus y squared. Okay. Okay, do you agree with that?
Yes.
Okay, so this is going to be 2 times delta. I'm going to let that be epsilon. So therefore, I'm going to say that my delta needs to be epsilon over 2. Okay, now let's do the proof. Let epsilon be greater than 0 be given. Then there exists delta, which is epsilon over 2, such that the absolute value of x to the fourth plus 2x squared plus 2y squared plus y to the fourth over x squared plus y squared minus 2. That is equal to the absolute value of x to the fourth plus 2x squared plus 2y squared plus y to the fourth minus 2 times x squared plus y squared all over x squared plus y squared. You agree? Found a common denominator.
Mm-hmm.
This was not easy. I ain't gonna lie.
Yes.
Girl, I had to figure this out. This, huh? I figured this out. Okay. So now that is equal to the absolute value of x to the fourth plus y to the fourth divided by x squared plus y squared. But we've already shown that that thing is less than or equal to 2 times x squared plus y squared. I think I screwed up. Hold on a minute. I got the wrong delta. That's 2 delta squared. Delta has to be the square root of epsilon over 2. Let me think. So this is less than or equal to 2 times delta squared. But delta squared is the square root of epsilon over 2 squared. That gives you epsilon. Okay, wrong. So epsilon delta has to be the square root of epsilon over 2. Okay, and then it is less than epsilon. Woo, there we go. So yes, so after all that we have proven, so the limit as xy approaches 0, 0 of f of xy is equal to 2. And then the third part of the continuity test, they are equal. The limit as xy approaches 0, 0 of f of xy is equal to f of 0, 0. So 1, 2, and 3 imply that f of xy above is continuous at xy equal to 0, at continuous at 0, 0. Forget all that. Ooh, that was not easy, but we did it. Okay. All right. If I had not defined, so now in this problem, if I had not defined the limit, this value, so if this is not given, if f of 0, 0 equal to 2 is not given, then the function will not be continuous. The only thing that made it continuous at 0, 0 was I gave you the function definition and I also proved the limit. Without that, it would not be continuous. Okay. Do you have any questions about this stuff here?
No, but I might have questions tomorrow.
Okay. We are a little ahead, I think. Actually, that's a good thing for us. Yeah, we're a little ahead. Today is the 19th, and I'm actually finished. So we're only a day ahead. That's all. I want to start partial derivatives. They can be kind of hairy, scary. So I'm going to go ahead and start that.